This is part 2 of solar electric design of off-grid or standalone do-it-yourself systems. We will be covering inverters and component sizing for a particular system. What I mean by component sizing is how many solar panel watts do you need for a particular battery bank and what should be the amp rating of the charge controller. An inverter converts DC to AC, and that AC can be either a sine wave like it normally is from the grid, or it can be a modified sine wave. Sine wave inverters cost more and are less efficient than their modified sine wave counterparts, although some appliances like mini microwave ovens will not work from a modified sine wave inverter. If you use a cheap multimeter to measure the voltage of a modified sine wave inverter, it will read lower than the actual voltage. These are a couple budget-friendly inverters that have been tested for low RF noise, one modified sine wave and the other sine wave. So if you're a ham, then you just need a quiet environment for your radio to operate in. These might be candidates for you. The rule of thumb that I use to size the inverter is to multiply the battery amp hours times 9 to get the recommended wattage for the inverter. Round this up to the nearest available inverter. This generally will be a robust size that will handle inrush motor currents. If you know exactly what your AC loads are, you can oftentimes get by with a much smaller inverter. Just keep in mind that the inrush motor currents drawn by freezers, refrigerators, sump pumps, and any motor-dependent device will briefly draw many times its running wattage when it's first turned on. So let's start putting the pieces together. Ideally, we would start by figuring out the load we want to power and build our system around that, but I'm going to start with a simpler approach first. That would be starting from a specific battery size and working your way to the solar panels. Knowing the battery we want to use, we can figure out what the charge current should be for that battery. For lead acid, we'd take 10% of the amp hour rating of the battery, and then we'd round that up to the nearest standard charge controller rating to determine what size charge controller to use. Then figure out the watts of power that will be going into the battery at that charge current. That charge wattage is what the solar panel wattage needs to be at a minimum. Then use the rule of thumb, 9 times battery amp hours to size the inverter. So let's run through an example. If we have a 225 amp hour battery, 10% of 225 is 23 amps of charge current. The charge controller rating just above 23 amps is 25 or 30 amps. It wouldn't hurt to go to 40 or 50 amps for the charge controller if you want to leave room for expansion. Convert the charge amps to charge watts by multiplying the battery voltage by the charge amps, or in our case, 12 times 23 is 276 watts. Ideally, that's how many watts our battery needs, so that it's how much the solar panel needs to produce. You can round this up to 300 watts of solar, as long as you don't exceed your charge controller's amp rating, or you can round it down to 250 watts, but it will take longer to recharge your batteries. The last item is the inverter, where we will apply the rule of thumb, battery amp hours times 9, which is 2025. The nearest standard inverter size is a 2000 watt inverter. So, not hard, right? Except we glossed over some issues that will make our system work better if we account for them. Those issues deal with efficiency losses for each component. This will not matter so much for small systems, but the larger the project, the more it matters that those losses be taken into account. In a best case scenario, we will suffer about 60% loss of potential power produced by the solar panels. That's while using lithium battery, MPPT charge controller, and no inverter. If you use a high efficiency inverter, add another 20% of loss, which is wasted as heat inside the inverter. So now we have lost 36% of our solar panel's output before it gets to the intended load. Lead acid batteries charge somewhat efficiently when deeply discharged, but get very wasteful as they near a full charge. So we are wasting over half our solar panel's energy with this configuration. A lead-acid battery bank that is configured to recover quickly will not deeply discharge, which puts us at about 2/3 of our solar panel output is wasted. Let's walk through a design in which we account for the losses. As before, first figure out the charge current based on the battery type. Second, multiply the charge current times battery voltage to get the charge wattage. Then round the charge wattage up for efficiency losses by multiplying it by a loss coefficient to get the solar array size. Then divide the solar array wattage by the battery voltage to determine the peak potential current that could come out of the charge controller. We round that value up to the next standard size charge controller. Lastly, we use a rule of thumb for the maximum inverter wattage equals battery amp hours times 9. So let's put some real-world numbers to that process. As we calculated before, the charge wattage for a pair of T105 batteries is 276 watts. To account for solar panel, wire, and MPPT charge controller waste, we round the 276 watt value up by multiplying it by 1.14 to get 315 watts. If we actually buy a 315 watt solar panel, we would figure out the charge controller size by dividing 315 by 12, that's the 12 volt battery voltage, to get 26 amps. So 26 amps is the most we would ever expect the charge controller to put out. The next higher standard size charge controller is a 30 amp, so we would buy a 30 amp charge controller. Inverter size is still a rule of thumb that previously came up with a 2000 watt inverter. Let's double our battery bank and run the numbers again. If we have 4 T105 batteries wired in a 12 volt configuration, then the total amp hours is 450. At 10% of the amp hours, the recommended maximum charge current is 45 amps. Multiply that by the battery bank voltage of 12 to get a charge wattage of 540 watts. Adjust for losses to get the recommended solar array of 620 watts. If we buy 6 100 watt solar panels, that's 600 watts. To figure out the charge controller size, we divide 600 by 12, that's 50 amps. The Victron charge controller can take a little overclocking, so it will work. This charge controller has a 100 amp maximum input voltage. So to keep the open circuit voltage under 100 volts, we can't series all of them, but we can series half of them and then wire those two strings in parallel to end up with a 66 VOC. Our previous practice design started from the battery and built out. We could have started from the electrical load and worked toward the battery, but the math is a little simpler going from the battery to the solar. The problem is we don't know if the battery will handle the load we want to power. For example, if we power up a chest freezer, it may draw 110 watts when running, which is easily powered by the 2000 watt inverter that we came up with in the previous design. But this freezer uses 1000 watt hours of power over a 24-hour period. The question we need to ask is, will the 225 amp hour lead acid battery be able to last all day under that load? We need to figure out how many watt hours of usable power our 225 amp hour battery contains. To do this, we multiply the battery bank voltage of 12 in this case times 225 amp hours, which gives us 2,700 watt hours of power. That's more than 1,000 watt hours that our freezer uses, but a lead acid battery should not be drained below 50% of their capacity, so that only leaves us with 1,350 watt hours of usable capacity. That's still enough, but we have a couple more areas of wasted energy for which we need to account. There is an energy waste in motorized appliances which is measured by its power factor. The kilowatt hour meter on the side of the house ignores this form of waste because the power company compensates for these losses before it reaches their generators. But if we are powering our freezer from a generator or inverter, then we are our own power company and we are going to get hit with that extra wasted power. My chest freezer, for example, has a power factor of 0.9, which results in a volt amp value of 122 volt amps instead of 110 watts. So we're going to treat volt amps as if it were watts so we can account for the power that is being drawn from the generator or inverter. When we apply the power factor to the 1000 watt-hours of the day's energy, we need to divide the freezer's load of 1000 watt-hours by 0.9, which gives us 1111 volt-amp-hours. Think of this as 1111 watt-hours, which is less than our 1350 watt-hour capacity of the battery. That would be enough, except we have one more source of power loss of which to deduct. An average inverter will waste about 1/4 of the DC power that it uses, so to account for that, we divide the freezer load of 1111 volt-amp-hours, which we will treat as watt-hours, by 75 to get a true load of 1481 watt-hours. Now we are over discharging our battery by 5%. If we can charge the battery while it is being used, as we do with the solar system, we could still use the battery bank without going over the 50% depth of discharge. All these losses still don't account for the greatest loss, which comes from getting the lead-acid battery to take a charge. Efficiency varies depending upon how deeply discharged the battery is taken down to, but a 40% waste of the charger's power is not uncommon. You can see how this is getting to be too complicated for most do-it-yourself types to get right. That's why I put together an Excel spreadsheet that automates all these calculations. You can download my Solar Battery Calculator Excel file from one of these two links. The top Fallbrook Amateur Radio Club site only works in the US. The lower site is a Dropbox link hosted by prepperwebsite.com. It is free and there are no strings attached like, asking for your Social Security number. If this all seems too intimidating, then you may just want to buy an all-in-one solar generator. I put together a comparison of 14 of the most popular solar generators in an overview that will help you narrow your options. Just do a YouTube search for Plan Bravo solar generator. Okay, I think that's all I've got, so thanks for being one of the few that made it all the way to the end, and God bless.